Hey guys, I'm just going to show you guys how to do number 6 on 5.3. A lot of people seem to be having questions on exactly how to do that. So I got my work right here, but I'm going to put it up on the board. I'm just going to show you this just so you can kind of see roughly how much it usually takes up to kind of do it well. Well, let's go ahead and put all of this on the board so you guys can see. All right. All right, as per usual, you should drop all of your notes on the ground and entirely lose your place. You have to do that. That's standard. Oh, here we are. Okay. It says it's a driveway, so I'm going to go ahead and just make that into just kind of a generalized ramp right here. Let's try to make it big enough for you to see. And it tells us that the angle of that particular driveway is 20 degrees. We have a car starting up here. And I should probably do a force diagram in this particular case. Force gravity goes straight down. Force normal goes perpendicular to the surface. That's probably not long enough, but I'm too short. And force friction goes straight back. Okay. It doesn't tell us about any other forces, so here we are. It tells us that the mass of this guy is 2,000 kilograms. It tells us it starts from rest. You don't have to write that down, but it's a good thing to write just so you kind of remember that for later. It tells us that force friction is 4,000 newtons. Okay. And then the displacement, or it says the length essentially of the the driveway is 5 meters. And the question is, how fast is it going at the end of the driveway? Okay, now let's start off with talking about this. I've regularly commented on the fact that you should not draw a displacement on your force diagram. That being said, if you're struggling quite a bit with this, specifically with the angle, it might not help you early. It might help you a little bit early on to do that. If you're gonna do that, I highly suggest using another color so it's very obvious that they don't necessarily belong with each other. There should not be a force down, but there is a displacement. Displacement is a straight line arrow from where it starts to where it ends. So I'll draw this in blue right here, where it starts to where it ends. That is displacement. Okay. If you can use your imagination to kind of remember this, that's better, because obviously you can see this can be kind of confusing later on to think, what is this force right here? It's not, it's displacement. They don't necessarily belong together, but comparing the two is obviously helpful in this chapter. All right. Now, since it wants to know what is the speed at the very end, I'm just going to start off with the equation that we're supposed to start in this chapter. Work net equals the change in kinetic energy. To fill this out, as we've already said, the work net is simply, I'm just going to look at all of my forces and assume that all of them do a work, which is not entirely accurate. We'll see that here in just a second. Do them in any order, doesn't really matter. The right side of this, the change in is always the same. That's Kf minus Ki. Now what I'm going to do is I'm going to zero out things that I know are in fact zero. This is where this guy comes back into play. I know the initial velocity is 0, so there is no initial kinetic energy of motion. That goes to 0. I'm also going to show number 7 later on. That is not the case for number 7, so make sure you're not always making that assumption. Work of normal, you'll notice up here because of my displacement that the angle between normal and displacement is 90 degrees. The easiest way to remember this is the fact that force normal is perpendicular to the surface and the displacement or the car is going parallel to the surface, which by definition are separated by 90 degrees. So that is 0. All the rest of these should do work. Like I should be able to look at gravity here and pretty easily see that gravity is going to add energy in this case, and that friction is going to take some of that energy out. And all of the extra energy should go into the energy of its motion. All right, from this point, I'm going to fill out individual equations. The equation for work is, oops, let's put W again. The force of gravity times the displacement times cosine angle of gravity, plus the force of friction times displacement times cosine theta of friction, equals the equation for kinetic energy is 1/2 mass speed final squared. Okay, a couple of simplifications that you can make here. Okay, number one, instead of writing force gravity, we know that's equal to mg. Now you do have to somewhat be careful of that if the problem had given you force of gravity. Don't put mg and then multiply by g in that case, but we do have m. So that's why we're just going to put mg right here. Okay, next, careful necessarily canceling out angles when you think there's supposed to be 1 or 2. This guy will get you into trouble in a second. But if we come over here to friction, you can see that the displacement is down the hill. The friction is back up the hill. They're separated. They're opposite directions. So this is 180. So this guy is going to go to -1. Another simplification you can make, I won't here probably, but you certainly can if it's easy, is you'll notice that the displacement is here and here. So it can be nice to not have to write it multiple times. You could factor that out in front. So you only have to write it once if you want to do that. Okay, we can't cancel it because there's no displacement over here. From this point, I'm trying to find speed. So I'm just going to do some algebra. Okay, so I have mass times gravity times displacement times cosine of angle of gravity. I'm going to bring this minus up front here, minus force friction times displacement. And then I'm going to multiply the 2 across everything. So that will cancel over here. And on this side, we're going to have a 2 on top. I'm going to divide mass by everything, which will cancel over here. And it's the same thing as me dividing mass right there. And then I'm going to square root both sides. If you are comfortable with the speed of that particular algebra, you can in fact go from this step to the other step. I'm usually able to follow that. If you're not comfortable, if you have to take multiple more steps in between, that's completely fine. You'll want to be doing this with letters. Now let's go ahead and punch the numbers in. So this is going to be 2 over 2,000 kilograms times 2,000 kilograms times g times 7.5. You'll notice me regularly putting this in parentheses just so I can separate it from this is the force of gravity and that is the displacement times cosine. And as I mentioned earlier, this is kind of a hard one. Remember that the angle is measured from the force to the displacement. Normal was easy, 90 degrees. Friction was easy, 180. But how about this guy? Well, that is somewhere between 0 and 90. I can see that it's definitely less than 90 if I make a horizontal right there, but I can't automatically just put 20 degrees in. What I can do is notice that because of alternate interior angles, this horizontal to the line is 20 degrees, and therefore this horizontal to the line is also 20 degrees. And from horizontal to vertical is 90 degrees. So that means this angle right in here is 90 minus 20 or 70 degrees. From this, I'm just plugging stuff in. Force friction over there is 4,000 newtons. Displacement is once again 7.5 meters. When you're getting up into big amounts of room like this that you're putting in, it's probably really important to organize. So instead of parentheses here, I'm going to put brackets just so I don't accidentally make some sort of mistake. Whole thing is square rooted. And that should spit out my final answer, which if you plug everything in correctly should be 3.68 meters per second, or just about 3.7 like the answer says. Let me know if there are any questions.